I had a bit of a dilemma with this talk, just too many slides, and so it's always hard to cut stuff away, and what I decided to do instead was use the drink from a fire hose approach, which is to just leave them in, and there are a whole bunch of slides which only need 10 seconds, and that's all I'm going to give them, and so the burden is on you that if you see something go by that you want me to stop and dwell on, just yell. Make some audible noise like pause, stop, whoa, something like that, so that I'll know that you'd like me to dwell there. You'll see a few of these are just, I didn't want to delete them, but they really only take a few seconds. Okay, so what motivated this talk is I mostly live in a C++ world, but I do have clients who are still using just C. And what I found is a lot of them are still using C90 with just a little bit of C99 thrown in. And so every so often I get somebody who's interested in knowing, well, what am I missing out on? And so this is going to cover things that I think, it's not a completely exhaustive set, but these are things which I think are interesting. Also, if you live in the C++ world, it is interesting, just as a student of languages, to see the different sensibilities of the C standardization effort and C++. And so that, I think, even if you live in a C++ world mostly, it's still kind of interesting to see. Because there's a fair amount of cross-pollination that occurs, where something originates in C and then winds up in C++, and vice versa. Okay, very briefly, here's the timeline. It's that there really have been 4 standards for the C language. C89 and 90 are essentially the same thing. 89 was the US standard, and 90 was the international version of that same standard. So most of us just refer to it as C90. C99, then 2011, there were substantive additions. Probably the biggest incremental change was between 90 and 99. 11 then added a bunch of other things, and then 18 is essentially just 11 with wording changes, refinements. There's supposed to be no feature changes. It's similar to the situation in C++, but having to do with C++ 03 and 98, which are essentially the same language. One thing that I think is very interesting is a philosophical attitude that is much more prominent in the C standardization effort than in C++, which is that they have I think, a greater concern for not breaking existing code. In other words, if something is compiling with the current generation of compilers, the C community tries harder to make it that when the new standard comes out, the old code still works. And that manifests itself particularly in the treatment of keywords and new identifiers. So what I'm talking about is this, there's a set of headers. It's about 40 standard headers. And they all have well-documented identifiers that are published there. So if you include, for example, standard io.h, everybody knows you get EOF and file and printf and things like that. But you also get the possibility of a handful of names that you don't know about. One of the common examples is that the data type file is often implemented as a typedef, which is an alias for some structure type, whose name you're not supposed to know. But the problem is, how do you avoid inadvertently creating a name that's spelled the same that could cause a compilation problem? Another example where this crops up is that there is a rule, with the exception of the header assert.h, the idea is that any header should be allowed, standard header should be allowed to be included more than once, and in any order with respect to the other standard headers. And there's a common idiom for implementing this, which you all know, which is to use include guards. And the problem is that the include guards require identifiers for the names of the macros which are used in the include guards. So, and the problem is, if you inadvertently use one of those names, you're going to have compilation problems, and there is a standard way of staying away from those names, and that is that the standard has this notion of reserved identifiers. And the idea is that there are rules for forming identifiers that the standard says just don't use these. And it's your obligation as a programmer to know what those rules are. And fortunately, the rules are pretty simple. One rule is that any name that begins with an underscore and a lowercase letter is reserved for use at global scope. Turns out you're allowed to use these names as structure members and local variables. You're just not allowed to use them as global names. The other category of reserved identifiers are things that begin with 2 underscores or an underscore and a capital letter. And those are reserved absolutely for all uses. You just never invent your own names with that spelling convention. Now, here's how this impacts you. This is observable behavior that you can see in the standardization effort. And one good example is the way that C treats the Boolean type. Originally, C didn't have a Boolean type. So it was common practice among C programmers who had experience in any other language to fashion their own Boolean type. C programmers who had only known C thought that Booleans were integers with the values 0 and non-zero. But those of us who have multilingual experience, how can you get by without a Boolean type? The problem was people would conjure up the Boolean type differently. Some people made it a type def, in which true and false were macro definitions. Others made it an enumeration type. So that when C99 added the Boolean type, they had to make sure that it didn't break code. And so they used a reserved identifier for the keyword. In particular, the name of the standard Boolean type in C that was added in C99 was underscore capital B bool. And the reason for that was that this was a name that was in the pool of reserved identifiers, which means that if you had been using this, you were already writing a program with undefined behavior. And the standards attitude was, now you get what you deserve. And so they could safely use that as the new type. And so it was a reserved identifier, now it's a keyword. And you'll see this pattern in a number of the other features that we're going to discuss. So if you want to use the more aesthetic spelling, which is bool all in lowercase, you have to include a header, standard bool.h. And when you do, not only do you get bool, but you get false and true. And the C standard took this approach because they say, if you know that you can get these names now added to your program without any conflict, go ahead and include standard bool.h. Now, interestingly, C++ couldn't take this approach. C++ had to make bool a keyword. And the reason is that the overloading rules in C++ say that if we had just used a type def, then that's not a unique type for the purposes of overloading. If we want to be able to overload on bool, it has to be a clearly distinct type. And so they say, okay, can't figure out how to do this other than to make it a keyword. And so you see that the C++ language, for legitimate reasons, couldn't be quite as deferential to existing code as the C language has been. Now, one of the other concerns that the C++ community had was, we'd like to know whether or not you're compiling with a standard C compiler. See, when C90 came out, that was the first standard. And so one of the questions that people would want to know is, well, am I compiling now with a standard compiler? Or do I have to do some things to dance around the fact that I'm compiling with a pre-standard compiler? So the way this was handled in C90 was to introduce this macro called _ standard std_c __, whose value was either 0 or 1. And you could use these in conditionals in order to be able to say, can I rely on all the features of standard C? Now, this is a classic example, though, of not planning ahead, because the next standard came out with new features, and immediately the question wasn't, is it standard or not, but which standard is it? And so they solved that by introducing another, they didn't get rid of std_c, they added another one, which is std_c version. And this is what you use to, for the most part, std_c is now not particularly interesting. This is the one that is interesting. And this is also, there's something like this in C++ as well, because C++ has to deal with the same issue. And the choice of the values for std_c, the macro, is a sequence of digits, a long integer essentially, whose numeric value is the month and year in which the standard came out. So that 2017-10 is the date that it is considered that it's actually the C18 standard came out. Some of the insiders actually refer to it as C17. But those of us involved in standardization process know that there's a lag between the time the committee says we're done and the time the ISO hierarchy finally puts the stamp of approval on it. So you can test, am I compiling with C18 by comparing the macro std_c version to that value. And you say, well, if it's not C18, is it C11? And if it's not C11, is it C99? And if it's not, is it at least standard C? And if it's not that, then you say, well, I'm dealing with something really ancient here. And so you can ask that question in the form of an if-def like this. Now, C99 has a fair number of features which are in common with C++. In some cases, they're identical. In others, there are minor variations. And I'll try to point out those variations as we go. The first one is the / comment. That's an example of a slide which merits 3 seconds or less. The long integer types, the extended integer types, relaxed declaration ordering, and declarations in 4 statements. Let's just hit each of these really quickly, and you'll stop me if you see anything that you'd like a question. Now, by the way, inlining and complex arithmetic are also things that C shares in common with C++, but there are clear differences, which we'll take a moment to point out. There we go. / comments. The thing I want to say about this is my understanding. I was on the C committee way back in the 80s, but when they got around to, after they finished the C90 standard and were looking at what do we do for the next standard. By the way, the common practice is that many of these standards committees release a standard and then they sort of go dormant for a while. I think the obligation is that they have to meet again within something like 5 years to decide. The question is, do we keep the standard as is? Is it now obsolete and nobody cares about it? Or are there certain things we'd like to add or tweak? But as we've seen with the C++ committee, there's just a never-ending churn of activity. They don't, who wants to go to sleep for a little while? We've got so much to do. That hasn't been, and so the first thing that the C committee did was they started to look at the list of things that C++ had added and said, are there any of these that we would like to borrow and incorporate into C90, C whatever it is after C90. And it turned out that every single feature was controversial except one, and that was this. This one, it was I think unanimous. Let's just do it. Other than that, this requires no additional elaboration. The long integer type, I believe that it originated in C and was borrowed over into C++. It's not just the addition of, that you can now say long instead of just long. And it wasn't enough to just add the type. The type required some additional support from the library. In particular, functions like A to L, or the labs function for computing absolute value, had to be augmented to include LL versions of those functions. Also, things like printf and scanf had to be augmented with format specifiers, and that was the extent of the support for that. Exact with integer types. Most people know about these, but there's an aspect of it which is worth pointing out. And this trait is also common with C++, which is that, as you all know, there's a certain amount of implementation-defined slack in the sizes of all of the arithmetic types. And it's an aid to portability in a lot of respects, but it's also a real nuisance for people who have specific range requirements. They need to know what's the range of values of an int. And so it became common practice early on for people to invent their own fixed width types. And it was such a common thing that finally the standards committee said, let's just standardize a set. And the set they standardized was placed in a header file called studint.h. And C++ provides essentially the same header and is common in this case. The names that are in the C99 version are all global names. In the C++ version, which is C studint, the names are all members of namespace std. That's the essential difference. And most of you are familiar with the int and uint underscore t names. And the set covers everything from 8 bits, 16 bits, 32, and 64, variations of signed and unsigned. Here's the interesting thing. These types are optional. It's that if you include studint.h, you are not guaranteed to get the full set. It's reasonable to expect to find something, like uint 32 and int 32, but you're not guaranteed to get int 8 or int 16. And the reason for that is that C and C++ aspire to be languages that compile for a wide range of target platforms. And one platform of interest are digital signal processors, which often have word sizes which are not as small as 8 bits or 16 bits. It's not uncommon to see a DSP with a 32-bit word size or a 64-bit word size. And that's the smallest addressable unit on the architecture. By definition, a byte in C and C++ is the size, it's an object whose size is the smallest addressable unit. It's, by definition, has size of 1, but it's not guaranteed to be 8 bits. It could be 16 or 32 or 24 bits, something like that. So that's why this set is not guaranteed to be everywhere. Now, if you have an 8-bit processor, which is common for most desktop workstation, you're going to get them all. But if you're concerned about writing highly portable code, this is an assumption that you can't make. So what do? Well, the header provides the int least data types. And just out of curiosity, how many of you have seen these before? Only a small number. Well, here's something new you just learned, which is that there are these types, int least 8, int least 16, int least 32, and 64. And what this is, you use these when you say, I only need to represent n bits, but I'll take the smallest thing that will hold that. So that if you don't need it to be exactly 8 bits, what you do is you say, I want int least 8. And you might get 16 or 32 bits allocated to the storage unit, but you'll get 8 that you can use. Now, the one thing, though, is you're not guaranteed when you use these types that the arithmetic that you use on those will behave exactly the same as the exact width types, because when there's overflows, it'll actually propagate into the higher order bits that you didn't ask for. So you do have to understand that that's what you're getting. You're not getting something that's a larger allocation with the exact same behavior as the exact width type. You're just getting a compromise that you then have to program carefully. But it does give you the ability to write, it gives you a slightly greater chance of writing standard portable code to do this. And these types are required. They are not optional. You're guaranteed that they will be in the header. The other set of type defs that's related to this is int fast n, or uint fast n. And what does this represent? This says, I would like to do arithmetic in n bits, and I would like it to be represented in the storage unit in which it will execute the fastest. You say, well, why isn't int fast 8 exactly 8? Well, classic example is the RISC processors like the classic ARM architecture. They have a decided bias toward 32-bit arithmetic. If you declare entities which are 8 bits, what the code wants to do is take the 8 bits, convert it into a 32-bit register, which requires a move and a sign extend. It does the arithmetic in that format, and then stores it back into exactly 8 bits by chopping it down. And you can easily do experiments with compilers on that kind of a target and find that choosing the exact width type actually incurs a performance penalty for certain kinds of arithmetic. And that if you say, I want the int fast 8 version, it'll just give you a 32-bit entity to store that, and you'll find that you don't pay the penalty for the expansion and contraction of the data type, getting it into the exact width size. So this is often, or potentially, a good choice for things like a loop control variable, where you know that the index value is still in a limited range, but you say, but I want it to run fast. You know, it would be inappropriate, though, to use these things for structures in which you have to have precise storage layout. Okay. Again, these things exist in both C and C++ in more or less the same form. Other extended integer types, there's an int max and a uint max. And this is saying, I would like an integer that will hold the largest possible value. Whatever this architecture will deal with. You say, now, isn't that long int and unsigned long? No, not necessarily, because it could be on a given architecture that long integer is 64 bits. But there is an underscore huge int, which is 128 bits on that platform. And since that's not standard, each compiler might give that large integer type some other name. Or they might support long int, which is a non-standard data type. And this is a portable way of saying whatever that integer type is, I want it. Int max and uint max. Another one is int putter, uint putter. And this is, I would like to have an integer which is big enough to store all the bits in a pointer without losing information. Sometimes, hopefully not very often, you need to be able to do arithmetic other than just adding and subtracting on a pointer. You want to be able to do operations like divides or multiplies because you're doing some hashing or something like that on a pointer value. And you can't do that natively on pointers. Pointers, all you can do is add and subtract. So you say, I want to convert it to an integer. What is the appropriate integer type that I can convert it to without losing information? The answer is it's int putter or uint putter. Now, this is an optional type, and that's because there may not be an architectural guarantee that, if it turns out, for example, that the size of a data pointer, a void star, is larger than the size of int max, then there is no int putter or uint putter. Right? There's no integer big enough to hold a pointer value without losing data. But pardon?
Does such a platform actually exist?
I can't name one, but I don't think the standards committee did this simply because it was a hypothetical. I suspect that such architectures do exist. Okay. Another feature is underscored func underscore. And this is the way that you can ask at compile time, what's the name of the function that I'm currently compiling? This is useful for doing tracing and error messages. And it's not a macro. It's actually an implicitly defined local object. Right there in the middle of the slide, it shows you what you can expect the definition for underscore underscore func underscore underscore to look like. It's actually a statically allocated array of characters initialized with a string literal whose value is the name of the function. And this is, if accessed, this will be defined for each function that refers to double underscore func. Now, you can only do this inside the body of a function. You can't refer to this in other scopes. And here would be a use for it. It's, for example, you could define macros that support doing runtime tracing of each time you enter and leave a function. And what it does is it simply prints out a message that says, I'm entering this function with this name. And you can just put the enter and leave macro calls inside the body of a function like foo or bar, and when you run the program, you see a trace. You probably want to make this conditional, but yes?
You need to use the printf for the present essay, or could you just use string concatenation if this was a...
I think you could use string concatenate.
Right.
Oh, I'm sorry. Func is not a macro. So yeah, pardon? Yes, it's actually the name of an object. So you would have to wrap func in another macro to get string concat, and by the time you get done with that, you'd say, okay, it's not worth the effort. Okay, let me just... Okay, what's next? Relaxed declaration ordering. This one was a no-brainer. Originally, C90 had the old style where all declarations had to be at the beginning of a block. Syntactically, they treated declarations and statements as distinct things. C++, this was introduced because it allows you to practice the good habit of delaying the declaration of an object until you're ready to initialize it. And so C language said, hey, there's really no reason to continue that old rigid style. Let's just borrow that idea. And then it followed that it made sense to do this for for loops as well. The old C90 style was, again, to put the declaration of for loop control variables at the beginning of a block and then initialize them that way. And now C90 uses the C++ approach with the same modern scope rules, which is that the scope of a loop control variable it ends with the closed curly brace. It ends with the body of the controlled statement. And so that's just the same as C++. Inlining is also a feature that C99 borrowed from C++. A classic example is, doing something like that. You want to test, is n an even integer? But that's not a self-evident computation. I mean, it's not too hard to reverse engineer it. Good habit would be to give it a name, but you don't want to pay a price for that. You'd like to get the same code quality. There are all sorts of justifications for wanting to do inlining. And the traditional way of doing this in C was to use macros, which had a number of negative effects. One of the principal negative effects was that macro calls don't behave exactly like function calls, in that if the arguments to the macro call themselves have side effects like pre and post increments, and the expression that represented the argument value was referenced more than once in the body of the macro, then something like *p++ would be applied more than once in that execution, and you would not get the same computed value as if you had used the function for doing that. And so inlining has the nice property that when you define a function as an inline, it has the same semantics as a non-inline function in a couple of ways. Interestingly, inline in C99 is not underscore capital inline. It's inline the same way it is in C++, and I'm not quite sure the rationale for that. It's interesting to me that it wasn't done the way the others were, but I double-checked it. It is a keyword. And so what happens is, as you well know, with inline calls, basically it takes the body of the function and substitutes it at the point of the call. But it's not just a textual substitution the way a macro is. What happens is it will do what it has to do in order to guarantee that the function still has, the inline function call has function-like semantics. So in the case of something like calling the max value with star p plus plus star q plus plus, we want to make sure that the side effect of the plus plus is only done once. So a compiler would guarantee that it would evaluate star p plus plus and capture that value in a CPU register. And it would do that for both star p plus plus and star q plus plus, and then use those in the evaluation of the comparison expression. So that's one of the big improvements of inlining over macros. The other one is that you can take the address of an inline function. Inline functions are functions. And you can take the address of a function that's well, you can do it even if it's inlined. Have any of you ever done that? Just out of curiosity, how many of you knew you could do that? This is behavior in C++ as well. So this is nothing different. And so the question is, what happens when you take the address? And the answer is it generates a non-inline copy of an inline function. Now, it doesn't turn all uses of the function into a non-inline function. It only happens when the call occurs through the pointer. In the other situations, the compiler is still going to try to evaluate the function call as an inline. Yes?
How do we do that in multiple compilation units?
The question is, what happens in multiple compilation units? I'm going to answer that question in a slide or two. That's a good question. So let's just talk about how inlining affects packaging. Typically, when functions are not inlined, by the way, the default, I talked about this in my lecture yesterday with having to do with storage duration and linkage. If I'm telling you anything here which doesn't quite sit right, go watch the other talk when the video comes out. The typical way that you package non-inline functions is that you put function declarations in a header file, and you put the corresponding function definition in a .c or in C++ a .cpp file. By default, these functions have external linkage, which means that they can be used for communication from one separately compiled translation unit to another. If you were to place the entire function definition in a header file and include that header in more than one place, then you would have problems not at compile time, but at link time. Because the compiler would observe, oh, I'm not the compiler, I misspoke. The linker would see, hey, that same function is defined in more than one object file. And what you would get is a link error which says the symbol is multiply defined. All that's expected behavior. However, with inline functions, you do go ahead and put not just the declaration, but you put the definition in the header file. Now, if the function is never called in a way that forces the compiler to generate a non-inline copy, all that's going to happen is the compiler uses that definition at the point of each call to simply substitute the body. No harm done. But the question is, what happens if, for example, two separate translation units decide to take the address of that function, and the compiler says, oh, I got to generate a non-inline call. How many copies of the function am I going to wind up with? Am I going to wind up with a copy in each translation unit? And the answer in both C and C++ is you still wind up with only one non-inline copy for the entire program. The official terminology, we say that non-inline copy has external linkage, and that no matter where the call takes place in any translation unit, they wind up going to one single copy. It's not, so the compiler doesn't regard that as multiply defined. Now, in C++, this is all handled automatically. Basically, you just go ahead and put your inline definition in a header file, and you can include that in as many separately compiled source files to produce object modules. And at link time, the linker is smart enough to recognize that the non-inline copies are permitted duplicates. And it throws away all but one. And it's all done automatically. But in C, my understanding is they didn't want to burden the linker with that additional smarts. So if you think this is going to happen, this is where C and C++ treat inlines differently. It's that in C, what you have to do is you have to pick the spot where you would like the non-inline copy to go if it gets used. And the way you do that is, in one of the .c files, you write a declaration, but not a definition, for the inline function to say, if a non-inline copy is to be generated, here's where I want it to be. So it's interesting. It's kind of backwards from the way you do it with non-inlines, which is with a non-inline, you put the declaration in the header and the definition in the source file. Here, you put the definition in the header and the declaration in the source file. Now, and so, by the way, if you want, you can put the word extern on that, and it's benign, it doesn't hurt. So doing it either way in this .c file would work. You can even say extern inline if you prefer that stylistically. What you can't do is just put inline by itself. That will get the compiler upset. Okay. So to a large extent, inlining is the same in C and C++ with this exception. Now, if you go ahead and try this, for example, with the GNU compiler, my experience is GNU is more permissive. And you may find that you can go ahead and get it to build without this. But it is my understanding that that's non-standard. They're giving you C++-like semantics in a C environment, which GNU does that in a number of ways. The default, I believe, for many GNU distributions is that the GNU C++ compiler will throw in some C features, which are not standard C++, just because, well, we've got them, here you can use them. And you have to actually go out of your way to turn these things off. You have to look carefully at the command options to say, no, give me just C. Don't give me C augmented with some niceties from C++. And when I was developing the tests to verify this stuff, I had to go and find those kinds of options because I would do stuff like this and find GNU is compiling it and I don't think they're right. And you drill down and you find out, oh, they were being nice to you and looking the other way while you did something that was non-standard. Okay, another feature is complex numbers. The C99 added support for complex arithmetic in rectangular form. So you can represent x plus yi, where I is the imaginary number. They do it with an extended keyword underscore capital C complex, and you can control the precision of a complex number. You can do float, double, long, double. You can also declare, in C, you can have, optionally, you can have just imaginary numbers. In other words, a representation of a number with no real part, only an imaginary part. Now, complex is required. The imaginary ones are optional. Not all C implementations have to support that. Now, in contrast, C++ doesn't have this as a built-in type. It's done with a template. You get a lot of the same functionality, but if you want to write code that's compatible in both languages, you have to do a little bit of dancing around, the type names are a little different. And C++ doesn't support a purely imaginary type. I'm not aware of that implementation. And by the way, just like it doesn't matter whether you say unsigned int or int unsigned, it doesn't matter what the order, double complex, complex double, same thing. It supports all the arithmetic that you expect it to support. And notice again that the type name is underscore capital C complex. So if you include the header complex.h, then you get a more attractive spelling, a lowercase c without the underscore. And the constant complex underscore I that's the representation of the value of the imaginary value 0 plus 1i. And then there's also versions like that for imaginary and underscore imaginary I. And then there's also, if you include complex.h, you also get a definition for the symbol capital I. So that's a name conflict you might want to look out for. Right? Not a lot of us name variables or functions that way, but I could imagine that one might be used somewhere. Okay. And of course, it's a built-in type. It has a reasonable set of conversions between the complex types and the floating types. And not surprisingly, if you convert a floating point number into a complex number, it just assumes that the imaginary part is 0. If you take a complex value and convert it into a floating value, it simply truncates the imaginary part. So most of this stuff does reasonably what you expect. And there are functions like cReal and cImag that allow you to extract the real and imaginary parts, and there are also well, actually, there are no, I don't think there's a format specifier specifically for displaying the real and imaginary parts. You have to extract the real and imaginary parts and display them as floats. Okay. Literals, let's talk about those for a moment. The syntactic construct called a literal are things like, well, 1 or 10 or 123, that's an integer literal. Quote, X quote is a character literal, or a double quoted sequence is a string literal. And, but if you invent a user-defined type, suppose I want to come up with a representation for rational numbers, where I store a numerator and a denominator, and I'd like to have the value 1/2 or 1/3. You can't do that on the fly in C90. You actually have to make a named constant, like 1/2, equal to, and a brace initialized value. And in C99, now you can do this kind of stuff on the fly with a notation as shown there in the highlighted red, where you can just put the name of the type rational in parentheses, followed by a brace enclosed initial value list. And this is what's known as a compound literal. And so that's an unnamed object, temporary object of type rational, whose structure members are initialized with a 1 and a 2. And that looks similar to something you can do in C++. Now that C++ has curly braced initializers, you can do things like that look similar, but turns out that doesn't compile as C++. C++ wants you to get rid of the parens around the type. So you'd have to write it that way. So it's close, but not quite the same in these two languages. You can also have on-the-fly literals of an array type. So for example, there, I want to have an integer array with so many elements in it. You can essentially write a type name, int square bracket m, where m is some constant value, and then have a brace initializer, and that will on the fly create an array with those elements in it. And not surprisingly, you can omit from inside the square brackets the dimension, and the compiler will figure out what the dimension is based on the number of elements in the initializer list. Again, this is similar to something you can do in C++, but C++ doesn't like those parens around the type. What you'd have to do in C++ to do something equivalent is come up with a named type, like digits, and use the name without parentheses in front of it, in front of the curly braced initializer list, and do it that way. So it's a similar capability, but not identical. Okay, that's compound list. Designated initializers. One use case for this, I think one of the principal motivations is that when you define unions and you want to be able to initialize an element in the union, in C90, you would put, for example, define a glop G1 inside the curly braces there. It would take whatever that value was and say, okay, that's the initial value for the first variant within the union. There was no notation in C90 by which you could say, no, I don't want to initialize the int, I want to initialize the double. And so in fact, if you put the 12.3 there, which looks like a floating point value, and you'd say, okay, that means I'm going to be initializing the double with that value. No. What it would do is take that 12.3, throw away the 0.3, turn it into an integer and use it to initialize the int member of the float. I'm sorry, yeah, the int member of the glop, I misspoke. And in doing that, you probably get a warning about a truncation error, but you're not mandated to get that warning. So with designated initializers, you can put a dot and the name of the member equals, and that will, now you can select which member of the union you want to initialize. That's a designated initializer. And these are going to be in C++20. They haven't been in C++ yet, but they will be coming to a compiler near you. Another use for these is, suppose I have a structure type like date, and a date represents a day, a month, and a year. The problem is that the North America, at least the US conventions for the order of these things are different, like so much. You know, the US insists on doing it differently than everybody else. And so we would, in the States, most people would put the month first and then the day, but most of the rest of the world puts the day first and then the month. And the problem is, without designated initializers, you could easily get them out of order and not know that you've done it wrong. But if you use designated initializers, you can have a slightly higher assurance that you put together what you want. You can also use designated initializers with arrays. So, for example, I've got this array with 10 elements, and I want it to be zeros almost everywhere, except for some values in the middle or at the end. And you can just put square bracket 3 to say, I want the the element with index 3 to be initialized with an 8, the element with index 7 to be initialized with a 2, and everything else will be zeroed.
And the 0 is guaranteed?
If it's statically allocated. I think it doesn't matter. I have to check the rules on that, but I believe it's zeros even for an automatic object. Okay, so here are some C99 features that are not in C++. One of them is variable length arrays. And in C90 and still in C++, when you declare, I should say define an array object, you have to give the dimension. And that dimension has to be expressed as a constant expression, meaning it can be an expression with multiple operands and operators in it as long as the whole thing can be evaluated to get a value at compile time. It can't be a runtime variable. And this is a problem if you have a function, for example, like this function f, which wants to be able to say, well, I've got a parameter to the function which represents the number of elements that I want for an array. I want to just have a local variable of an array type with that many elements. And that was not native to C90, and it's not native to C++ either. So you had to do something like dynamic allocation, which then, of course, imposes the burden of remembering to clean up after yourself, something that's easy to forget to do. And so it gets even worse if you have multi-dimensional arrays, because you would have to do a more complex computation to compute the size of the allocation. Plus, when you go to index the elements, you can't use multiple square bracketed indices. You have to do the arithmetic to treat it as if it's a single dimension array. This was a recurring problem for people who did arithmetic on arrays, array elements. So with variable length arrays, you can now do this. You can just declare a local variable of an array type, and the dimensions can be non-constant. And the compiler imposes on the runtime system the responsibility of allocating the storage for that and deallocating it automatically. That's what's called a variable length array. And I didn't look carefully at very many implementations, but these are probably not on the stack. These are probably managed dynamic. Yes?
Yeah, I think maybe GCC uses stack sometimes. I know other compilers use heap.
Yes.
And I know other compilers, if you don't have any memory on your heap,
Mm-hmm.
your processor will crash.
It will crash, yes. So the implementation is not specified as to where that storage comes from. It's a matter of the runtime system deciding whether it will use heap or, I mean, it's smart. You can often do this stuff with stack allocation. So what you want to do if you are going to use these things is investigate the allocation and deallocation strategy. And the nice thing is with the VLAs, you can, especially with multi-dimensional arrays, you can use multiply dimensioned subscripting, and it will do the correct offset computations for you. Okay, and you can also have VLAs as parameters. Not only, so they're allowed to be local objects and they're allowed to be parameters. They are not allowed to occur outside of block scope. So you can't make these things global. Now, the other thing that happens is size of, which for every other data type is a compile time computation, size of becomes a runtime computation for VLAs. It's not guaranteed anymore to be a constant expression. As I say, VLAs can only appear as function parameters or in a function body, and they can't be external or static. They can't be statically allocated. Interestingly, this was in the GNU compilers early on. It's hard to find another C compiler that supports this. So much so that when C11 came out, they reclassified it as an optional feature. It was kind of like a big, oh, never mind. And in C++, it doesn't exist. The expectation is you're going to use vector. Now, flexible array members, here's a use case for this. Suppose that it's not uncommon in communication software, for example, that you have packet structures where you have a fixed size header followed by a variable length tail. And so how do you represent that? Well, you want to be able to have a structure which has some fixed layout header and then an array of a variable dimension. And the problem is you can't use a variably dimensioned array in this context. And so the common idiom prior to C99 was to simply say, okay, I'll just pick 1 as the dimension of that array. And then I'll just allow the fact that C doesn't do bounds checking and go ahead and allocate something bigger and pretend there's a bigger array there. Now, the thing is that when you do it this way, you have to be careful about how you compute the size of the total object that you allocate, because you say, okay, if I want to have a packet with n bytes in the trailing portion, what I'll do is I want to malloc the size of the header plus n times the size of data. Actually, that should have been a data sub 0. I think that's a typo. I want the type of, not the whole, in this case, so I think it should have been size of data sub 0. Or I could have just, Oh, no, I misspoke. Data is the data type, so it's n times size of data. That is correct. The problem with this strategy is, drum roll, yeah, it's the presence of possible padding bytes, because if the data requires alignment, the compiler is free to put padding bytes after the header, before the first element in the data portion. And so what you have to do actually is compute not the size of the header, but the offset of where the data portion is. And you can use the standard offset of macro to do that. So it was a trickier computation, easy to make a mistake. And so the C99 solution to this is to use what's called a flexible array member, not to be confused with a VLA, in which you can just use empty square brackets as the dimension of the trailing portion of the packet. And this is what's known as a flexible array member. And so now the computation is that the size of the packet includes any trailing padding bytes that might be there. Okay? So that's how you work with those. Another feature, restrict, keyword restrict. This is another type specifier like const or volatile. And you see this now in the declarations of functions in places like standard live.h and string.h. And actually, yeah, that's a mistake up there. It's not standard live.h declares store copy, it's string.h. But and strict is really intended for the declaration of pointer parameters. That's, even though it's syntactically like const or volatile, it really doesn't have any use other than for what you see there. Now, what does this mean? Why is this there? It's because pointer aliasing can create problems for optimizers that want, especially on architectures that have vector operations. And in order to be able to use optimizations which might use vector processing instructions, you have to have confidence that the operands to the vector operations are non-overlapping. And so essentially what a restricted pointer means is it's permission to the compiler to say, go ahead and assume that this pointer is the only pointer pointing to that entity, and that you're allowed to freely reorder operations to optimize vector operations without worrying, gee, is the source and the destination overlapping, in which case I would care about not reordering things. It allows the greater caching and things like that. And so that's what restrict is used for primarily. So that you'll see, yeah, I'm going to wrap up here, that the standard standard definitions for these functions now have restricts in them. And now what happens is if you go ahead and pass in operands that do overlap, the behavior is undefined. It's your responsibility to make sure that you've passed in data that does satisfy the restrict constraint. There are functions like memmove, which don't have the restrict there because memmove is defined to work for possibly overlapping operands. Let's just see if we have. And so I'll just mention this and wrap up at this point, which is that you know that declarations which have array parameters with an empty square bracket, it's essentially just a pointer. And when you declare things which are arrays of const or arrays of volatile, you can do them either as pointers or square bracketed arrays. The problem is that if you have a parameter which is a constant pointer, there wasn't any comparable array notation. You can do it now in C99 with putting the const inside the square brackets. Now I'll tell you though, that's not very useful. Turns out that the real use for that is to be able to put the restrict in there. So be able to use array notation and say that this is an array that's restricted. Okay, and I think that's as far as we'll get. I had a few more, but I think I'll just leave it at that because somebody else has to speak in this time slot. So I hope you found this useful. Thanks.